simplify the data and define the whole water quality based on the score between 0 and 100. So a higher score reflects the better water quality. And with this approach, obviously there are some limitations that it depends on the data, expert judgment, and threshold. But overall, that's the main goal. We have to communicate that. So just going a bit deeper, how we're gonna use this technique. As you can see, F1. I'll start, putting something on the screen. Okay, where is that? Okay, so yeah, so F1. So, okay, just give me a second, please. Okay, where is that? Yeah, it's working, I think. Clear our drawings. Sorry, guys. Okay, yeah. So F1 is a scope. What it represents is, it quantifies, the percentage of the parameters. Parameters means water quality parameters that doesn't meet the guidelines. So basically, guideline can be for any country or any place, and it's very flexible. So you identify how many number of parameters failed in the total number of parameters considered. That's scope. What is the broader scope? When we look for the F2, it represents the frequency. How many times a particular testing fails. Similarly, F3 is the amplitude, which defines how much is the how much factor it has, it doesn't meet the guideline. So these are the formulas. I mean, I'm not going to go into the details, but I'll try to I have put some example to explain how we're going to calculate it. So if I move to the next slide, this is example. I mean, just to give you guys a heads up. So this is, a typical water quality testing report. We have, let's say, DO, pH, total phosphorus, total nitrogen, fecal coliform, arsenic, lead, and all those. So we have those, data that has been recorded, sampling and monitoring, and we have the guideline on the bottom. At the bottom, you can see that. So how are we going to calculate the index of this? Like there are, 10 parameters, and all of them have been reported in different ways. So as an environmental engineer, you will understand, okay, these are the parameters, some are meeting the guidelines, some are not. But if you have to present this whole thing to someone who is from a management background or who is from a different background, how are you going to do it? One approach is you're going to do the average. Second approach is you're going to, put some discussion. So this indexing approach simplifies the whole concept. So you can actually quantify the whole, whole idea into one number, and that can be presented as high, medium, and low, or any number. So if you look at F1 on the bottom, it's written 2 out of 10 into 100, which is 20. So how 2 out of 10? So if you can notice on the table, I again try to write something. Let's see if that works this time. So you can see here. Can you see the screen? I've put something. Yes, yeah. So this is 0.058. I mean, you can see it's higher than this guideline, 0.05. So that's 1. So that means in total phosphorus, there is some, exceedance from the guideline. And similarly, if you notice here, this value was higher. There are other values as well. So basically, out of 2 parameters, like total phosphorus and this one, out of 10 parameters, 2 failed the test. So F1 will be 20. In the second one, we have all these numbers that in total, they become 1 or 3. So in total, this one, and this one, these 4 doesn't meet the guideline. Rest of them are okay, but these 4 doesn't meet the guideline. So these were 4. So 4 out of 103 here, that makes F2 as 3.9. So that's how you calculate or you try to map or communicate into simple way. Moving forward as a F3 in the next slide, just a second, please. Yeah, this one. This is how we calculate the amplitude, which is extrusion. And I'm gonna just simplify it. It's all written. I've placed the reference here, but just explaining a bit more in detail. So you can see here. So this is basically how much, the parameter which exceeds how much it's exceeded. So there's a certain formula. This is the value 0.058, which is the exact value, and 0.05 is the guideline value. So you normalize it, you calculate some score, which is, okay, yeah, which is something this like this 0.16, 1.16, 1.35, 0.275. These four values basically came from these all parameters. I'm just going to go back to the previous slide just to give you guys a heads up. So these four parameters are the ones which exceeded, which I mentioned, like this one, 0.058, 0.108, 0.0094, and 0.0051. Those four parameters which exceeded the guideline. We calculated these, exclusions for all these four, combine it, and calculate F3. I mean, there's a formula. And you can see on the bottom, if we combine F1, F2, F3, you get a certain score value, which is 88. Now, according to this method, 88 means the water quality is good. And obviously, it should be good because you can see on the parameter, only out of 1 or 3, only 4 times, only 2 parameters failed the test. In the rest of the time, the water quality was good. So you cannot actually see only those parameters, but you cannot only ignore them. So this is how these methods were developed, and this is how these methods facilitated in understanding the overall water quality. So you can now see this whole table, which is so complicated. Like, I'm not saying that for all of you, but if someone reads this table with no background about water, he'll get confused. But if you just present everything in just one number, which is on the 88, so everyone can understand, okay, that's okay, the water quality is good or water quality is bad. So that's how you manage it. Now, so this approach is very common. People have applied it, and still apply it. But this approach just merely gives everything on a number scale. Those numbers sometimes doesn't mean anything. Water quality is CWK score is 88. What does this mean? How you're gonna be using those scores to further improve the water quality? So that's why with more development, the concept of footprint came into being. Now, before jumping into the concept, I'm just trying to give an idea what is water footprint. Everything that we use, or everything that we consume for our betterment has an impact. Even if you apply a water treatment, it comes with the price of some impacts. It can have a impact. It can consume energy. It has some impacts with respect to chemicals or anything. So based on this, now globally, people are trying to quantify the impact of every activity they do, and they are trying to quantify on the scale of footprint. We have green water footprint, we have environmental footprint, we have carbon footprint. I'm sure most of you have heard these concepts. But what is this concept is? It's all about, anything you make, anything you produce, there is something that is making up. So it has an impact on environment, and that's footprint. So people, the water, or basically, I was about to say, the footprint community is trying to map all of these concepts into one scale. Let's say if you have a municipality or if you have a city, the cars might have a footprint. It can have a carbon footprint, energy footprint, or water footprint. Similarly, a house has a footprint, or even water treatment has a footprint. So when whole globe is going towards this concept, we as water engineers or environmental engineers need to see this concept and try to map our impacts, water quality challenges or pollution challenges on a scale of footprint. And for that, we need to understand what this virtual water is. How we understand footprint is, every product that is being produced, contains a virtual water, that produced in the back end in indirect way. Water might have used during its processing, during its consumption. So if water has been used and come back to the system, like, that's like a water cycle, that's okay. But what most of us do is, when we do the production, that water gets contaminated or gets polluted, and it doesn't get back to the system. And that's basically the water footprint is all about. So going into more detail, we have categorized water footprint into 3 categories, blue water, green water, gray water. It's not something we call a physical concept. It is basically it is a conceptual approach But in conceptual or in virtual way, you try to quantify which has the more impact and which has the less impact. And honestly, that helped a lot of the people in communicating their impact. So blue water is all about water consumed from the surface water, but water that is consumed and that didn't come back to the surface water back. Similarly, green water is related to the rain, and the most important is the gray water footprint, which is basically is based on the concept of dilution. That if, let's say, conceptually, if water is more contaminated, means you need more fresh water to dilute it, not actually, but as conceptually. So that means if you say that system has a high gray water footprint, means the water that is coming, or the polluted water that is produced, that system is producing, is either very highly contaminated or has a very much high load. So it's a simple concept, just like you are trying to pitch it in a different way. And that is all about the gray water footprint. So simplifying it, these are the three concepts: rainwater, green water, blue water, and the fresh water. Can you please all mute your speaker, please? It's all good. Thank you. Yeah. So there are three concepts: green, blue, and gray. What we'll be focusing is on the gray water footprint, but I'm just giving you a background, like how we use these concepts for the betterment of our society. So this is just an example, I kind of quoted. So you can see making a pizza. So making a pizza, we have to make a pizza, we need different ingredients. And for all these ingredients, somehow there needs to be a water, water from the surface sources, water from the lake. And while producing it, there's also some, waste that is generated. It's a basic concept, but, try to map it on a footprint scale. So even the making a pizza has some footprint. It has a footprint in terms of blue water, green water, because a certain amount of water has been used, and that water doesn't go back to the system. So even the impact is minimum, but just making a pizza, and now you can quantify it on a scale, like how much water footprint of the pizza making is. It can be any number. It doesn't mean that there needs to be no footprint. There is the footprint, but we need to see how much impact on water resources we are putting in this concept. And similarly, if the making a pizza has, there's some chemical use to produce flour, or, to produce mozzarella, or to produce something. So the more contamination, the more gray water is. So first two, the blue and the green water, as you can see on the top, are the consumptive water use, and the gray water is all about a degraded water use. So based on this concept, all around the world, people have now tried to quantify it. And this is a very interesting research topic because people are trying to quantify the impact of each activity, which includes from making a coffee, tea, soda, water, beef, how much impact it has on the environment. And that's very important. I mean, this is a very simple concept, but understanding it is very difficult. On the other side, for us, we say, okay, making a soda has an impact. Now with a scale of footprint, you can actually quantify it. Now you can see on the picture, I'm sure most of you understand which product is having a more impact, which is having a less impact. That's how easy the communication can be. Otherwise, if someone starts, okay, how much is the impact of producing beef? They're gonna start making discussion, and maybe it can confuse anyone. So it's all about the communication and quantifying on a common scale. And based on this concept, I move towards this concept of gray water footprint in drinking water quality management. So on the left side, you can see a dilution concept. I think most of you have done this series dilution in environmental microbiology. So this is the dilution means you dilute the contamination to a certain point where the contamination is no more. So you can see in the first colony, the ratio is very high. In the last one, the ratio is very high, less. So what I did, now coming up to my topic and briefly giving you a discussion, I try to quantify the water pollution in drinking water, drinking water system on the scale of gray water footprint, which has never been done before. And interestingly, when as water engineers and environmental engineers, when we go to some management or some decision makers or some politician, we say, okay, this is high, this is low, we need a treatment plant. That's one thing. But in order to communicate to them, like how much this activity, this treatment plant or this treatment unit is gonna impact the environment, and you can easily give them the numbers on the scale of water footprint. Like this treatment has high water footprint, this contamination has low water footprint. Trust me, that will help most of the people, because they will see their footprint, their activity footprint. They can correlate like which activity is sustainable or which activity is necessary. So gray water footprint, which I use, is based on the concept that the pollution, any contamination that can be arsenic, iron, disinfection byproduct, comes on the top of natural water body. And it is just based on a simple ratio, which I developed, is gray water footprint equals V into C1 over Ca, where V is the volume of water that is produced from a system. C is the contaminant, any contaminant or a group of contaminant exposure. I took the median value. Ca is the acceptable exposure. So this equations merely look very simple, but there's a huge calculation on the back end. So basically what we are proposing is volume. Any system can have a high volume, low volume. So that can be applied on any system. So volume of water, if the distribution system is higher, V value will be higher. Distribution system is less, has a less population, V value will be lower. Similarly for C1 and Ca, the concentration that you are considering, you can consider like a bunch of 100 parameters, or you can consider 5 parameters. You can consider their higher value or medium value, that's up to you. But overall, you are trying to map the ratio, that simple dilution on a scale of gray water footprint. So basically you're considering the volume, the quantity, and the quality. And if you try to link with the distribution system goals, we need to provide the water with good quality and quantity. And that's how we are trying to use a simple concept to present our idea, or to present our case. So these are the key steps that I adopted. I'm not presenting the details about this, because obviously if anyone is interested, you can read the paper. But overall, it's all about mapping it. And most of you can even use this concept in your researches, in your consultancy report, wherever it's applicable. So I identified the different strategies. Strategy means water treatment systems that are being currently applied in Canadian municipalities, and identified what are the contamination concerns. So I assessed their whole thing using this water footprint approach. I got the results and validate. Validate means, compare the results with the established approach, that is the Canadian Water Quality Index, which I just explained. That has been established 20 years back, and it's very applicable globally. So I compared my approach results with the results that most of the municipalities are doing to present their water quality, and try to estimate how much impact even a water treatment facility is causing to the environment. How much impact, if we say one contaminant is very less, but we think it is less, but when we try to quantify it, we say, okay, what gray water footprint it does have, and it happens when we do the assessment. So again, dating back to my concept, it's very important to quantify it. Treatment is one aspect, and that's very important. I agree. Like when we are growing and we say, okay, we have to develop a treatment system that's going to change. We need to physically quantify. We need to actually quantify, this particular aspect and try to map it. And what I did is basically just simply mapped a water pollution on the scale of water footprint and compare the result with some established approaches, which is the conventional indexing-based approach, the Canadian Water Quality Index, and try to see how much this new approach is, the results are how similar the results were. And fortunately, the results were very similar, and somehow, the approach that I kind of developed became validated. The benefit of this approach, I'm not saying that the previous approach is bad or something. I'm not the one to claim that. It's all about, this doesn't help to quantify, like, is there any municipality has a high grade water footprint, means there is more water pollution or contamination. But on the other side, you can correlate water pollution based footprint to other footprints all around the world. So somehow you can quantify the impact of a certain activity, particularly in the water, with other activities that are globally occurring. And that's what the whole picture is all about. So just a brief summary, I kind of took 6 drinking water quality management strategies. These are actually applied in Canadian water systems. One system has, chlorination, filtration. Some systems have coagulation, flocculation. I'm sure most of you know these techniques. So their source water, I collected the data from all of these, studied that. I just didn't simply apply the CA over CV. There's in addition, I use the human health risk assessment techniques and some Monte Carlo simulations, data forecasting techniques to basically collect the data with numbers of more than 1,000, with more than 1,000 number units, try to compile it and assess how much the water quality is. But the benefit that I got is, as you can see on the picture, it's not only to assess the drinking water quality, but also to estimate the pollution level and to communicate the impacts of deteriorating water quality on society. And I did the validation of results. So I just give you the highlight of this whole approach, but in actual, there's a bunch of calculations that were going on in the background. But those calculations doesn't mean the most important is the concept, like what we are trying to achieve. And that's what I kind of did. These are the few steps that I adopted. I mean, the most important one is the second, the water footprint approach, which includes, water demand and dilution factor. Dilution factor is the one, basically, I mentioned C over C ratio. And on the left side, you can see in the Monte Carlo simulation generation, like I kind of combine it with a human health risk assessment. That helped me to, compile all the contaminants together and map it on the scale of concentration. So, I mean, if most of you are interested, you can go through the research and we can talk about it if you need any further discussion. The most important is after that is the results. So when I applied the approach for all the treatment systems, these on the bottom are the drinking water systems, and these are actual drinking water system. I mapped their performance on a scale of per capita and on a scale of overall. Per capita of gray water footprint and overall water footprint is just the same concept that I'm sure most of you guys know, like per capita water demand and a total water demand. So on the per capita scale, there were different scores. On the overall scale, there were different scores, and that's real because some communities are small, some communities are big. If the community is small, there's more possibility that each person is having more impact, is creating more impact. So, but the most interesting, when I try to compare this overall gray water footprint with the CWQI, the Canadian Water Quality Index score, the results were very similar. And why this looking different here? Because CWQI scores, the higher is the better. For gray water footprint scores, lower is the better. So you can see the last three in both have a more damaging impact. Moving forward, when I try to compare it, the results were pretty much same. That means the new approach on this one can be an alternative. I'm not saying it is an alternative, but can be a possible alternative to this Canadian Water Quality Index. But Canadian Water Quality Index itself is a very established approach. So my approach is new, and I'm not underlying any approach. It's just like seeing the world from a different perspective. I mean, both approaches are equally applicable, but in fact, CWQA might be better in a lot of ways because there's more testing. But it's just like thinking in a new particular aspect. So when we map the originality and contribution of this whole idea is develop a new water quality based water quality assessment approach, which on the scale of footprint. It can be a possible alternative to previously developed approach. Impacts of water pollution can be quantified, and the most important is results can be easily communicated beyond expert community. And that's what whole idea is. Assess and manage, as I mentioned in the motivation, is the most important step to do the control or to even see how you're going to future with this be looking like. We can think of developing the best water treatment system in the world, and that's fine. But we need to understand even developing a best water treatment system has an impact. And we need to understand whether our community or our system can afford that. Just like if we look into our country's profile, we have financial constraints. So you cannot adopt the best technique. But with this approach, you can quantify the cost and the benefit. And somehow you can decide a better treatment option rather than just spending billions on something which is unsustainable. So these are the references I used for preparing the presentation. I mean, you can obviously Google it and go through for more details if you're interested. And thank you so much. And if you have any questions, please, I'm open to the floor.
Thank you very much for delivering such an informative session. It was really, really helpful. Being environmental and water professionals, it was very like important for us to hear from you because you have touched a very important aspect of water monitoring in the distribution networks and like from different approaches. So anyone, if you have any questions, please feel free to mention it in the chat box, or maybe you can unmic question. Please feel free. And yeah.
Yeah, thank you so much for inviting me, Rabia, and your magazine. And I'm surprised still there are 14 participants. I was expecting maybe one or two. Like, I'm like, okay, I mean, this guy's just talking, let's leave. But thank you so much for staying. I mean,
No, sir, it's like everyone is so excited, and we are happy because when we upload it on the YouTube, I think like more than 200 people watch our lecture. We have seen the trend, so everyone is very interested to know about what going on, and especially they were really happy. Even like at 9:30 p.m., they were very excited to join.
oh, you must know, yeah. Just kidding. I mean, thank you so much, everyone, for listening. And I'm just going to post my email address on the chat box. If you have any questions regarding the research, you are feel free to reach out to me. I mean, I will just give you a very high level, idea. But I mean, if anyone is doing research or applying in their jobs or everything, you can see this concept and see how you can make it better. How you can use it for the betterment of the society. Yeah.
Sir, I have a question, like a very general one. Like, you know that nowadays there's a very emerging problem in Canada and America that is related with perfluoroalkyl substances. How do you think your research is related with the contaminants of emerging concern, like the contaminants that are really difficult, like people are really concerned that either they are being removed in the process or not?
Yeah. So,
Make it a little bit.
yeah. So basically, I totally understand. Basically, what I did is not like the state of the art. I mean, there's going to be a lot of improvements, and it's not the universal thing. It's been validated, but obviously more people need to apply and see whether how much this thing gonna be this thing is gonna work. But yes, this approach is very flexible. Why I'm saying it's flexible is because you can define your own guidelines based on the system that you are working on, and you can see the concentration of any contaminant and correlate with the set standard or guideline. And basically, even those emerging contaminants, you can, even if you have a data for those particular community, you can map those data on a scale of footprint, see how much the footprint is. So basically what I did is just an approach. So that approach is flexible. You can add either one contaminant, or you can even add the hundreds contaminant and see the ratio of all of these. So yeah, I think that can be adopted to their circumstances.
That's really very important aspect of that parameters and can check. That is really different from other researches in which we are very particularly focused that even if this treatment system is removing that contaminant or maybe that contaminant.
Yeah.
Or sir, just explain it like a little bit more for us that, for example, being in basically this magazine is focused on environmental sciences, engineering, and technology. So being an environmental engineer, when you were working in this sector in the water, how did you develop a thought process to do research on this topic, and how did you get an inspiration? Can you please share your one on convenience? Thank you.
Oh, that's a very difficult question. I mean, uh, okay. I mean, this type of question, okay, I have to think about it, but yeah, I mean, basically thought process is, in a very simplistic way, it's not something I'm not claiming something that I developed something that is, state of the art, or, it can change the world or something. When you read the literature, you should always keep two aspects in your mind. You're an engineer, yes, that's one thing, and most of us are, but being an engineer, you have to be a good manager. when we are growing up as an environmental engineer, and when we are in our bachelor's, first year, second year, third, fourth, and moving forward, we always think that we need to apply a very high level of treatment, and we're going to put the water, and the water is going to be like, okay, something, and you're going to be like, world is going to be very ideal for living. As a manager, you need to always see the long-term impacts or effects of those water. What my perspective was at the time, and still I am, is you can develop a treatment plant, and that can be developed for one time, but you can manage it for 100 years. And if you try to adopt this approach, I'm sure you're going to find a lot of ways to improve a lot of systems. Even this technique that I have developed, from the managerial perspective, you have to see how you can improve the world how you can make the world better. So that's the whole idea I can think of while while I was developing this approach, not only to see from the perspective of just and as an engineer, but also looking at the long term, how we can manage it in a better way. Yeah.
That's really amazing, sir. I think it would be really helpful for me as well, because like right now I'm working in the water sector with a water company, and we are designing water treatment plants. It would be really helpful for me as well, and I hope that this will be helpful for other participants as well. But thank you very much for such an amazing webinar and giving us your time. Thank you so much, and thank you for all the participants to join. See you next time, and I will be sharing the link of the recorded lecture on all the social media platform and via email as well. Thank you very much.
Thank you so much, everyone. Have a good night or day wherever you are.